Finite Element Method FEM-inspired Functional Biomedical Systems Modeling, number 1637, the 11th of May 2026, Gerald C. EclaireMD Foundation. Category: Research Methodology. Introduction. Recently, after reflecting more deeply on my viscoplastic energy methodology (VMT) and my post-stroke research work, I gradually realized that my research framework has already contained many important finite element method FEM concepts for years, although not in the traditional anatomical, geometrical, or structural material engineering sense. At first, I was confused because classical FEM normally requires detailed anatomical geometry, vessel wall thickness, elasticity, plaque structure, blood viscosity distribution, boundary conditions, and the conversion of partial differential equations into sets of algebraic equations in order to calculate local stress-strain behavior of a continuum structure. I do not possess those types of anatomical data from the medical domain. I do not have patient-specific vascular geometry, local vessel wall material properties, MRI angiography reconstructions, or detailed biomechanics measurements. Therefore, I cannot honestly claim that I am performing a true traditional anatomical finite element simulation of blood vessels or human organs similar to the classical structural engineering FEM methodology that I learned at MIT in 1973. Present medical research does contain some detailed anatomical and biomechanics studies for organs such as the heart, major arteries, brain vessels, bones, and aneurysms using MRI, CT angiography, ultrasound, and CFD methods. However, even advanced biomedical FEM studies still rely heavily on estimated parameters, such as vessel wall elasticity, stiffness, constitutive behavior, blood viscosity, and boundary conditions. Human tissues are not fixed engineering materials like in organic steel structures because they are organic materials which vary from person to person and continuously change physiologically over time. Furthermore, most medical FEM studies are organ-specific and short-term, while my research focuses on longitudinal whole-body metabolic behavior over 17 years. Therefore, my technical strength is not detailed anatomical geometry, but rather massive longitudinal biomarker data, key lifestyle trajectories, repeated loading history, and long-term nonlinear and dynamic systems. That is why my framework naturally evolved toward systems behavior, cumulative energy accumulation, trajectory analysis, and transition risk dynamics rather than local anatomical stress calculation. However, after thinking more carefully about the deeper philosophy behind FEM, I gradually realized that the most important aspect of FEM for my work may not be geometric meshes themselves, but rather the systems decomposition conceptual philosophy behind FEM. In classical engineering, FEM divides a complicated continuum structure into many smaller interacting elements in order to understand how the entire system behaves dynamically under loading conditions. The purpose is not simply geometric visualization, but understanding stress-strain interaction, state deformation, system instability, energy accumulation, fatigue behavior, and both path and time-dependent system response. Functional biomedical elements. I gradually realized that my VMT framework already operates in a conceptually similar manner to FEM. More precisely, during my data preparation stage, the concepts of both finite element decomposition and normalization were already unconsciously incorporated as part of my viscoplastic energy model. The major difference is that classical FEM uses geometric structural elements, while my VMT methodology uses functional biomedical elements. My elements are not small triangular or quadrilateral meshes inside a bridge or blood vessel. Instead, they are interacting physiological subsystems represented by biomarkers and lifestyle variables, evolving continuously over time. For example, my framework already separates the biomedical system into interacting functional components such as glucose regulation through FPG, PPG, and EEG, blood pressure behavior through SBP and DBP, vascular stiffness through pulse pressure PP, vascular loading through SBP, sleep recovery, exercise activity, visceral fat accumulation, stress amplification, metabolic recovery, and neurological adaptation. These functional elements continuously interact dynamically and collectively determine the overall pathophysiological behavior of the human system. Conceptually, this is highly similar to the finite element method. This recent realization became very important to me because I finally understood that my work was never truly attempting to model static anatomy itself. Instead, Since my first medical research paper published at UIDF on the 7th of December 2016, I was already modeling dynamic pathophysiological behavior evolving over time under repeated loading conditions. Longitudinal biomarker system. In classical FEM, engineers begin with continuum mechanics, material constitutive equations, geometry, partial differential equations, boundary conditions, and discretized meshes. The continuum structure is then divided into many smaller geometric elements, and the overall structural behavior is solved numerically through simultaneous algebraic equations. My biomedical system does not contain those types of structural equations or anatomical measurements, however. It does contain something else that may be equally valuable: 17 years of longitudinal biomarker and lifestyle data, millions of personal data points, continuous glucose trajectories, blood pressure behavior, body weight evolution, visceral fat changes, sleep patterns, exercise behavior, and post-stroke and neurological observations. Therefore, my system may be viewed as a discretized functional biomedical systems model rather than a geometric structural model. My biomarkers are not material constants in the engineering sense. Instead, they function as pathophysiological state variables describing dynamic loading conditions imposed on the biomedical system. SBP reflects a trigger of vascular loading state. Glucose reflects long-term metabolic loading state and damage K in my vascular structure. Sleep reflects stroke recovery modulation. Exercise reflects adaptive unloading and conditioning. In this way, the complicated and organic biomedical system can still be decomposed into interacting elements, although the decomposition occurs in functional physiological space rather than physical geometric or material science space. Normalization and time-step evolution. I also realized that my normalization procedures are conceptually similar to normalization methods frequently used in engineering FEM and systems dynamics. By normalizing glucose, SBP, visceral fat, sleep, exercise, and other biomarkers, I can study relative loading intensity and interaction behavior independent of absolute scale. For example, normal SBP reference equals 120 mg. Normal pulse pressure reference equals 45 mm. Normal fasting glucose reference equals 100 mg. L normal EG reference equals 120 mg. L normal BMI reference equals 25. Instead of attempting to calculate exact arterial stiffness, I estimate relative loading conditions such as SBP loading index equals measured SBP 120 pulse pressure loading index equals measured PP for 5 glucose loading index equals EG 120. If SBP equals 150 mmHg, then the SBP loading index becomes 1.25, meaning vascular pressure loading is approximately 25% above the normalized baseline. If pulse pressure equals 70 mmHg, then the pulse pressure loading index becomes 1.56, meaning pulsatile vascular loading is approximately 56% above the normalized baseline. If EG equals 150 mg dl, then the glucose loading index becomes 1.25, using these normalized variables. A simplified vascular stress or stroke index may become vascular stress or stroke index equals SBP 120 xBP 45 xEG 120 under the above example equals 150 120ths x 70 45ths x 150 120ths equals 1.25 x 1.56 x 1.25 equals to 0.44. This means the combined vascular loading condition is approximately to 0.44 times the normalized baseline condition. Importantly, this is not a direct anatomical FEM simulation. Instead, it is an FEM-inspired functional biomedical systems model in which interacting pathophysiological subsystems evolve dynamically over our time under repeated loading conditions. Furthermore, my calculations already evolve step by step over time. Similar to incremental loading analysis in engineering systems, at each time step, the system state changes, loading conditions evolve, subsystem interactions shift, and accumulated history modifies future behavior. This resembles fatigue accumulation, viscoplastic memory behavior, creep-like behavior, and transient systems analysis in engineering mechanics. Relationship between FEM, VMT, and TSI. After thinking more deeply about this issue, I gradually realized that my methodology already contains many important FEM-style concepts, including system decomposition, interacting elements, dynamic loading, cumulative energy behavior, history dependence, normalization procedures, time-step evolution, nonlinear interaction, and global system response emerging from coupled subsystems. This realization also helped me understand why my VMT framework naturally evolved toward energy accumulation, trajectory behavior, fatigue-like loading, stress amplification, transition risk behavior, and long-term instability detection. These are fundamentally systems behavior problems rather than purely geometric problems. VMT behaves somewhat like a time-dependent cumulative loading memory system, conceptually similar to fatigue accumulation, viscoplastic deformation process, CREP behavior, or history-dependent structural behavior in engineering. Meanwhile, TSI functions more like a nonlinear instability or transition risk amplification indicator that detects when interacting biomedical subsystems begin moving toward dangerous TRAJCT or IS. Therefore, my framework may naturally separate into three layers. Layer 1, FEM-inspired functional systems. Decomposition involving interacting biomedical subsystems. Layer 2, longitudinal cumulative damage through VMT energy accumulation and fatigue-like behavior. Layer 3, dynamic transition risk trajectory through TSI nonlinear amplification and early warning gate. CTI. This layered structure may provide a scientifically honest bridge between engineering, structural modeling, and human biomedical systems. Post-stroke cognitive recovery. This realization also helped me understand why my recent post-stroke neurological recovery process appears conceptually connected to this systems framework. During the past 11 months after my stroke, I had intentionally constructed a very intensive form of cognitive constraint-induced therapy CIT. Traditional rehabilitation often focuses on speech recovery, walking, arm movement, balance, or simple memory exercises. However, continuous writing, cross-domain conceptual integration, high-frequency memory retrieval, systems modeling, audio thinking, and sustained concentration, this repeatedly activated memory networks, executive function pathways, language circuits, pattern recognition, structural reasoning, and long-term integration systems, instead of functioning as psychological stress. This intense cognitive workload appeared to function more like neurological rehabilitation. Remarkably, during this process, my SPP remained near or below 110 mmHg, fatigue remained relatively low, and research productivity increased substantially. Normally, advanced age, stroke history, seizure history, and prolonged cognitive workload would usually predict fatigue, instability, or cognitive decline. Instead, my case appears associated with stable physiology, high sustained concentration, continuous idea generation, cross-domain integration, and increased conceptual productivity. This may partially explain why both the stroke chairman and epilepsy chairman of neuroscience department at Stanford University became interested in studying my unusual neurological recovery pattern. From a systems perspective, my brain itself may have undergone continuous loading, adaptive reorganization, feedback reinforcement, energy redistribution, and structural stabilization. In some ways, my neurological recovery process may itself become part of the broader systems framework connecting FEM-inspired decomposition, fluid mechanics, pathophysiology, VMT, TSI topology, neuroplasticity, and longitudinal biomedical dynamics. Conclusion: after studying this problem more deeply, I gradually realized that I do not need to force my research into the strict framework of classical finite element modeling. Classical FEM mainly focuses on geometric structures, material properties, constitutive equations, and local stress-strain behavior. My biomedical research does not contain those types of anatomical data. However, my VMT methodology already contains many important FEM-inspired concepts, including systems decomposition, interacting elements, dynamic loading, normalization, cumulative energy behavior, time-step evolution, and coupled subsystem response. The major difference is that my elements are functional biomedical subsystems rather than geometric structural meshes. Therefore, my work is better described as a functional biomedical systems model inspired by FEM philosophy rather than a true anatomical FEM simulation. Instead of studying static geometry alone, I am studying how interacting physiological subsystems evolve dynamically over time under repeated loading conditions and cumulative physiological stress. This realization also explains why VMT, TSI topology, neuroplasticity, and longitudinal systems dynamics fit together naturally within the same overall framework. Therefore, I will continue developing my VMT and TSI methodologies as the primary direction of my future biomedical systems research. Epilogue: I have finally understood what Professor Norman Jones told me in 1974. His only true interests in life were teaching and researching, using education and knowledge to help change the world. He was never interested in fame, power, or money. Now, in 2026 at age 79, I finally understand myself better as well. Similar to Professor Jones, my deepest interest in life has always been knowledge, learning, and application to create useful products and help the world. Through my medical research, I hope to directly apply my learned knowledge to help patients better understand disease, improve health, and live longer lives. This is simply one example of my overall and very simple life purpose, knowledge, and application. Essentially, Professor Jones and I have shared a very similar and simple life purpose through education and knowledge, help students, product users, and disease patients. Life purpose does not need to be complicated. In many ways, the simpler and purer it is, the better. I believe this may also explain why I could gradually see the common thread connecting mathematics, physics, engineering, science, medicine, history, and society. The discovery that FEM concepts were already quietly embedded inside my VMT framework, together with topology and systems dynamics for biomedicine, is simply one working example of that deeper connection. It also seems to me that the secret to a concave upward life trajectory may be to remain a student forever, driven by a purpose so simple that it cannot easily be corrupted by external noise such as greed, vanity, ego, fame, power, or money. In many ways, I have unintentionally turned my own life into a living experiment of my VMT framework by continuously optimizing the flow of knowledge, learning, discipline, and useful application to sustain the overall system of my life. Perhaps that is also how I could gradually understand how FEM concepts naturally became part of VMT, and later how VMT became part of VPT. At the deepest level, I simply remained a lifelong student. Trajectory rises when intelligence and discipline dominate while external noise remains small. As greed, fame, ego, power, and money increase, the denominator grows and suppresses the overall trajectory. The long-term acceleration fx determines whether the trajectory shows faster acceleration, slower acceleration, or deceleration, resulting in either a concave upward or concave downward life trajectory. Reducing noise allows positive acceleration and a concave upward trajectory, while increasing noise leads to deceleration and a concave downward trajectory. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.